All right, so this is homework 6, question number 4. It's a pretty tricky one. I suggest kind of solving it in 3 main parts. Firstly, when we're going to be transmitting the power strictly at 120 volts, and then when we're going to be using that step up, step down transformer system. So that's 1 and 2. And then part 3 is going to be when we're finding that that change in power between those 2 options. So just so we're all on the same page, we have 80 kilowatts of power arriving to a town from a power station through transmission lines. The resistance of the transmission lines is given. How much power is saved if the voltage is stepped up from 120 volts to 30,000 volts and then back to 120 volts rather than just transmitting at 120 volts. So yeah, let's just dive into it. I'm just going to start with what I like to think of it as my first part in solving this. Part 1, that being transmitting when strictly at 120 volts. So let's see here. I have my notes right here. So I'm just going to call this part 1. That's how I like to think about it. You can see, right? Wait. So here we're going to be transmitting strictly at 120 volts. So essentially what we're looking at here is we have like a generator. There's the transformers, it's like kind of a null point here because it's just going straight, hits the resistor, and then hits town, right? That's just how I'm visualizing here. So in part 1, what we're going to do is we're first going to solve for for the current acting here. So we have, I'm going to actually call this Roman numeral 1, or yeah, Roman numeral 1, just so we're not going to get mixed up. So we have P equals IV, where this power is, it's the power of the town, right? Yeah, so it's the amount of power that arrives at the town through the power station. So we're just going to have to rearrange this to solve for I. So that's I equals P over V. And, that's 80 times 10 to the 3rd over 120. I'm not going to write that. But that comes out as 666 amps. We now have enough to solve for the power at that resistor because there's going to be a little bit of a loss here through this resistor. So we need to recognize that. So now using that current we just found, we can look for the power, R for like resistor, and use an alternate a definition of power, that being I squared R, where we now have I squared 666 amps. Square root of that times the given resistance, which is 0.02. What does that come out as? It's 8,888 watts. All right, and therefore we're going to be looking for some power total now of this system where it's strictly at 120 volts. So I'm just going to call that my Roman numeral part 3. I'm looking for my power total 1. What is that? That's going to be equal to my power used by the town, given in the question, plus the power. So essentially, like the first part of this, you need to just find that current that's acting here, so you can find the power that is going to be acted on by that resistor, or I should say, going to be lost by that resistor. So that will all come out to, I guess there's a lot of same numbers in every one. It's like 666, 88888 watts. All right. So that's part 1, when transmitting power is strictly at 120 volts. So following that, we can look at part 2 of this. I'm going to call it 2. Make sure we can all see here. Yeah, so that's 2. We're going to be looking for power saved by using step up and step down. Using step dash step down system. Kind of hard to see power in using step up slash step down system. So the first thing we can recognize is, actually, I'm going to kind of draw this out. So here we have a generator, right? This is just to like help you visualize. Here we have a generator. What comes out of here then goes through that transformer. How do we represent transformers? It's like with these bumpies. Alternate transformer, like that. There's a resistor on these lines. Resistor on these lines. Another transformer. And then we finally have, I'm going to call this my town. Right? So at each one of these steps, we can technically assign a power, right? We can say over here, we have the power of the town. I'm going to call that P town. Over here, I'm going to call this P1, here P2, here P3, here P4, and here P generator. So right off the bat, and if you have a good eye, you should just establish that like these two are going to be equal and these two are going to be equal, right? There's no transformer in between them, and there's like no resistor in between them. So we can now consider those guys equal. So I'm just going to write that. So my kind of part 1 here. So P town equals P1. And what's the relationship between P2 and P1? Well, actually, P2 is equal to epsilon, where epsilon is the efficiency of that transformer, which happens to be 99%. So as you're going to be able to see here, we're going to find that, let me just double check to make sure before I say this. Yeah. So P2 is going to expectantly have a higher power than P1 just because it's not 100% efficiency. There's going to be some loss there. So if we rearrange this equation slightly, we'll see that I'm just going to go forward with P town. P town, and then move epsilon to the other side, where epsilon equals 0.99 equals P2. At which point we can solve for P2 because, you know, P town given. This is just 1 over 0.99. P2 is going to come out to be 80 and another 80. Sorry, guys, kind of hard to. Right here. All right, P2 found. The next thing I'm going to want to work with is that current that's acting right here. I need that current that's acting right here to be able to solve for the power at that resistor again, right? Because I'm going to need to incorporate that, the power. I'm going to call it PR prime. Like the sum of these two will equal P3. So how do I find this PR double prime? I'm going to need to find the current here. How do I have a capacity to find that current? Is by using that P2. And also, we know the voltage at P2, right? Yeah, and that's because here, this is going to be our step up. I'm going to call that SU. And this is going to be our step down. I'm going to call it SD, right? So we know that it's going to step up to the voltage here. What's it, 3 times 10 to the 4. So the voltage here equals 3 times 10 to the 4, and then it's going to be stepped back down to 120. And I think it starts at 122, actually. Yeah, so now we have conditions to solve for that PR double prime. We can just set up our equation. So I'm going to write we're looking for that current there, so that's V2. And then equals I2. Okay. You're just going to do some quick rearranging. Oh, actually, we don't even need rearranging. You just need to plug in. We just found that P2 equals 80 and then divided by 3 times 10 to the 4. What does that come out as? 2.7 amps. All right. So now we have part 2 there. We can now find the power at that resistor, which the sum of that PR double prime and P2 will equal P3. So we're getting close to our end here. So how do we do that again? Through an alternate definition of power, where it's PR double prime equals I squared. I'm going to call it I2 squared. Because we found I1 previously in part 1. And then, times R. 7 squared times 0.02. What does this come out to be? 0.1458 watts. So it's obviously very, very little there, but we just can't forget about it, right? Because the difference between here and here, you need to recognize. So now we have enough to solve for P3. P3 equals PR double prime plus P2. Okay. We have both of these values. We just solve for PR double prime and we have P2 from before. I'm not going to bother rewriting them. But if you plug everything in, you're going to end up with 0.80808.15 watts. All right, so now we're getting really close to the end here. I'm going to jump up here and use this space so I can just keep it all on the same screen. So this is now part 5. Part 5. Sorry, I know I'm going out of order. I'm jumping, but just stick with me here. Wait, did I? 1, 2, 3, 4. Yeah, okay, part 5. Okay, so now we're going to want to find that P4. There's a relationship between P4, which also equals, P generated, right? I already told you why they're equal to each other. Equals P4. There's nothing acting between them. It's the same things. And there's a relationship between P3, where P3 is going to be less than P4, and we know it's 99% efficient. So again, where epsilon equals 99. Therefore, we do P. Wait, that's not right. One second. Oh yeah, okay. So the epsilon needs to be here, not here. Yeah, right, because P3 is going to be bigger. I mean, P4 is going to be bigger than P3, right? So now we can do P3 times 1 over 0.99. Yeah. Now P4 is going to come out with a bigger value. So P4 equals 81624, and it's like 0.2 watts. All right. So now we have that P of the generator in P4. We can compare that to what we previously found as P total 1. And we can find a change in power versus using a system strictly at 120 volts versus using a system which has a step up and step down properties. So if you'll allow me to just write down here, I'm going to call this my big part 3, and I write a 1. This is my big part 3 right here. I'm going to have some change in power because I want to find what's the difference, in using one system over. So I'm going to search for a change in power, and that's going to be equal to, this is what we got is P total 1. And then going to be minus what we just got as P4, which equals our P generator, which is like, the total power that is going to be there. So you can call it like, basically it's P total 2. So that's 81624. I can even write 0.2. And you can just subtract that now, and that will give you 7,263 watts. All right, so that's our final answer. And I have seen, like another student told me that this is different than what's on the key. Right now, I cannot find any other way to solve this. And this agrees with my multiple attempts and other students who even questioned me about it. So I presume here that maybe the answer key is wrong. But yeah, so that's how you solve this one. I think that setting it up like this makes it a little bit easier. And then just being able to see where all of our powers act definitely helps. Okay, so I'm going to wrap that guy up here. All right, thanks guys.